We're combining two units today on central angles and arc measures. A central angle is just an angle whose vertex is at the center of the circle. So for instance, over here on the top left, I could say that angle ACB, because C is the center, ACB is a central angle. And the key thing about a central angle is that it has the same measure as its arc. And so by arc, I mean a piece of the outside of the circle. So this, I could say, is arc AB. I'd write it like this, arc AB. Or you could write it out, arc AB. And the idea here is that an arc, the measure of that arc, is the same as its central angle. So the measure here of AB is 50 degrees. And that should make sense because if you're going all the way around the circle, whether it's a little, whether it's here or here or here, either way, you're going 360 degrees all the way around. So that central angle of 50 degrees is going to have the same measure as its corresponding arc AB, which is also 50 degrees. So because it's less than 180, we call this AB a minor arc. Okay, so now we could put another point, and I'll just change the color here to separate it. We could put another point, D, and actually I want to put it right here. We could put D on the circle. And we could go all the way around from A through D to B. So we could say A, D, B. And so we could say the measure and of arc ADB. And so notice because I'm putting the D there, we have to go around that way. And so that's just going to be 360 degrees less the 50. So that's 360 minus that 50 because we're taking that chunk out because we're stopping at B. And so it's 310 degrees. And since that's more than 180, that would be a major arc. All right, so the last thing I want to do on this diagram is what if we drew straight through, I'm just trying to find some other color we haven't used. What if I drew straight through the center to D? So because I'm going through C, I know that AD is a diameter, okay? And then so what if I wanted to do arc AD? And I know this is half of the circle, right? So measure arc AD. Again, I know it's half the circle because I'm going through, it's a diameter. And so I know that that's 180 degrees. And 180 degrees we call a semicircle. And then so the last thing on this bottom right, I just wanted to show you that we can just add up arcs. So when they say find measure of arc ABD, they're saying arc ABD. And this AB is 50 and BD is 60. So if we want the combined total, we can just add them up. So we know that that would be 50 plus 60, and that would be 110 degrees. So it's as simple as that. Okay, so next, if you have two circles and the radius is the same, so in this case you can see the radius there is 5, the radius there is 5, they're the same circles. So now if you have a piece of that circle that's the same, so in this case, this arc AB also has a measure of 50 degrees because it's the same as central angle. This DE, this arc, is also 50 degrees. And so if you have the same piece of two circles that are the same, then they must be congruent. So these two pieces are congruent. So you know that arc AB is congruent to arc DE. However, if you look at the smaller circle down in the bottom, GH does have a measure of 50 degrees, but it's a piece of a smaller circle because that radius is only 4. So that's a smaller circle. So GH is going to be smaller. Arc GH is going to be smaller. Even though the measure, the angle is the same, the actual length of it, if you took that as like a string and you straightened it out, it would be shorter. So you could say GH, that arc, is going to be shorter than either AB or DE. We'll just write it like that. Okay? Because that radius is smaller, so it's a piece of a smaller circle. However, if we look at the right, if you have two chords that are the same distance, so AB, chord AB, and chord CD are congruent. So if you have two chords that are the same length, then their corresponding arcs must also be the same length, because there's a relationship between the length of the chord and its arc that it's cutting off. So if this is the same length, CD, as AB, then these arcs must also be the same. So we know that AB, chord AB, has to be the same as arc AB has to be the same as arc CD. So if they gave you the measure of 1, if they said, oh, this is 110 degrees, then you know that this also would have to be 110 degrees. So if one chord, a couple more things, if one chord is a perpendicular bisector of another, then the first chord is a diameter. And this makes sense because if you look at, so we have AB here and we have CD, and this is, so we're saying this is perpendicular. We're also saying this is getting bisected. And if that's getting bisected, what it means is that AB must be running right through the middle. And if it's running right through the middle, it's going through the center. And if it's going through the center, then it's a diameter, right? So AB, chord AB, is a diameter. And if you moved AB, you could see, well, that's not going through the center, so this is still perpendicular. But CD is, let's call this E, right? CE is obviously not the same length as ED, and it makes sense because we moved AB. So if we moved AB, it's no longer going through the center, so it's no longer going to cut CD through the middle, and so that's not going to be a bisector of CD. So you can tell if it bisects the chord, it has to have gone through the center, so it has to be a diameter. And so we can take that same idea and apply it over to this problem here. So they want you to find the measure of AC, and AC is this chord right here. And so you notice here that BED is going through the center. And if it's going through the center, it's a diameter, and it must be cutting CA. It must be cutting this chord in half, which means that this CF must be congruent to FA. And so AC, well, so this must also be 7. So AC must be 7 plus 7, or 14. And then now find X. The same idea we were just talking about. If we have these two chords, if we have these two sections, if this section is the same as this section, then the arcs that it's cutting off, or it's corresponding to, that arc, must also be the same as this arc. So in this case, we know that 9x has to be the same as 80 minus x. And so we can just add that. We'll add the x to both sides. We get 10x equals 80, and divide by 10, and we get x equals 8. So if two chords are the same distance from the center, they are congruent. And this makes sense. Look, you have CD, right? And so you have CD, and that's a diameter. And notice as you get farther away from the center, these are getting shorter and shorter, right? CD is greater than EF, which is greater than AB. And so the only way you'd have two that are the same, like if you wanted one that was the same as EF, it would have to be about right here. It would have to be the same distance away from the center, which is exactly what we have over on the right here. We have AB, which is the same distance away as from the center CD, and I need to mark that actually. So we'll say that's congruent to that. You need to see that. The other thing is, notice how they measured it. These are perpendicular. Remember when we measure distance, we measure as a perpendicular line. It couldn't be at some random angle, okay? But if this distance is the same as that distance, then we know that AB is the same as CD. So they gave you some measure. If they said, for instance, let's say AB was 9, then you'd know that CD was also 9.